Okay, now let's look at the significance of SVD. So it is used in data compression, much like the spectral theorem. Remember, when we could write A as a Q lambda Q transpose, we could write it out as a sum of a series of matrices. Similarly, we can do it here also. We have U and UI coming from U, and then V transpose, or VI transpose coming from that. So UI, VI transpose, the size of that matrix, that's a matrix, it's a vector times a transpose of another vector. That size is going to be the same as the size of A, and then whatever comes out of the sigma hat, which will be just a scaling factor, sigma I. So that is a summation of matrices of the kind UI, VI transpose. Those are of the same size as A, and then there are R of them because the dimension of the row space and the column space is R, and so is the size of a sigma matrix is R by R. So if you think about the U vector, that is in M by 1, so M rows and 1 column. The V vector is actually in N by 1, but V transpose, so they should be transposed. That would be in 1 by N, so 1 and 1 will cancel, then you get M by N, which is the size of the matrix that you started with. So it's a rank 1 matrix because it's coming out of the linear combination of this one vector weighted by the weighting factors in the other vector. Okay, so it's a rank 1 matrix. So it's a rank 1 approximation. So if you take the first guy out of this series of R matrices, that is a rank 1 approximation. Typically in SVD, we arrange the singular values in decreasing order. So sigma 1 is going to be greater than sigma 2, it's going to be greater than sigma 3, etc. So the first one in this summation is going to be the most important rank 1 matrix that A decomposes into. So if you just take the first one, you get an approximation for A. It may not be a very good approximation. If not, you can just take the second one also, and if that's not good enough, then you take the third one and take the first few. At some point, you're going to be happy with the kind of approximation you got for the matrix A, and that would be a much smaller set of matrices to store. I'll tell you why. So let's look at the storage requirement. Let's say A is a 1000 by 1000 matrix, and A will take 1 million bytes of storage. But if you take rank 1 approximation, you will have 100 elements, V will have 100 elements, and sigma is just 1 element, so that is 201. So rank 1 approximation of that guy will be just 201 compared to 1 million. And if rank 1 is not good enough, the first one is not good enough, so you take the first 10 of them. So 10 of them will be 2010, so 2000 instead of 1 million. That is still a huge saving. So storage, as you can compute here, instead of M times N, the size of the original matrix, you need only M plus N plus 1 per term, I mean. So if you take K of them, so K times that number. So it's a much smaller number. So this is a data compression algorithm. But just recently, while I was writing this book, I wanted to see if it was still being used. And I found a paper that was written in 2017, I referred to it in the textbook, that actually uses SVD for image compression. The second one is much more important in terms of data science, which is the principal component analysis. Take any matrix, data matrix, M by N. Typically, M is much larger than N because many more observations than variables. If you take the mean of each column and subtract it from each element of the column, then that is called zero-centering the data. That means the data now in each column will have a mean of 0 because you just subtracted it out. And after that, if you take A transpose A, the DAM matrix, that is going to be proportional to the covariance in the data. If you just write it out, you will see that is actually the expression for the covariance because you're subtracting the mean. Then that is covariance times the number of observations. Now, if you do the EVD of A transpose A, which is the same as the SVD of A, singular value decomposition of A, remember, is the eigenvalue decomposition of A transpose A, then that gives you the linear combinations of the columns that will preserve the largest amount of variance as the first approximation. The second one will give you the second largest amount of variance. So that gives you a handle on the variance of the data coming from different linear combinations of the variables. And if you want to capture only a certain amount of variance, let's say you want to capture 90% of the variance in the data and build a model out of that, then you might need out of, let's say 100 features that you have, you might need only the first 7 of them or first 15 of them. So instead of 100 features, you might have only 7 or 15 features that you need to work with, and that will capture 90% or 95% of the variance, which exactly how much SVD will tell you. This is just the sum of the singular values divided by singular values up to the number k, 7 or 15 that you're thinking about, divided by the sum of all the singular values up to R, which is the rank of the matrix, which is going to be the same as the number of columns actually. That fraction will give you the maximum amount of variance that you can capture in your model. That gives you an upper limit of what they call the coefficient of determination. If you remember from statistics, coefficient of determination R square is a fraction of the variance that your model explains in the data. So that, an upper limit of that is given by the SVD if you're doing dimensionality reduction or feature engineering. And that is a powerful technique that is used in almost all data science projects as the initial stage. So you don't want to deal with 100 features, you want to deal with only 15 linear combinations of them. Those are the engineered features, and that might be good enough, and that might actually be better because it is possible that the linear combinations corresponding to small values of sigma are actually just noise, and maybe you actually want to get rid of them. So doing this selection of the most significant or the principal components of the data might actually give you a better model because you are improving the signal to noise ratio in your data. You're doing something like a low pass filtering. Okay, so that is a principal component analysis, and how it is done, and with an example is there in the textbook. This is something that you should look at. It is going to be useful. It is one of the principal applications of SVD, and it is in fact the starting point of many books on data science. Actually, there is a book that I referred to. That book actually starts as the first chapter, principal component analysis, or SVD, I think, and that is it, and that is the mathematical foundation of data science. So a couple of more words about this principal components. So you have a huge data matrix. You want the most important part. The most important is the principal part. So what are the principal components of the matrix? And the most important principal component will be the rank 1 approximation of the matrix. That is, in our decomposition of A as the sigma, as the summation of a series of matrices based on SVD, is the first one. Okay, and if you take the first k of them, that will give you a very good approximation of the data, and it might actually it might improve the signal to noise ratio because what you're ignoring might actually be more like noise rather than data. So let me actually summarize principal component analysis. We haven't gone into the details of it. It's a deep field. Every single subtopic in the last couple of weeks is actually a deep field. It's a portal to something that is fairly deep and rich. So principal directions are the vectors, the right singular vectors V, and the components, the principal components in the data are projections along the principal directions, which are actually linear combinations of the columns of A, taking V as the weighting factor. So V, the vectors Vi in V, is called the loading because those are the weighting factors, the scalars, that will scale the columns of A to give you the principal component, the second principal component, etc. So that is the loading, and AV or AV1, AV2, those are the principal components. And that by our equation, AV is equal to U sigma, so you can come at it from the other side also and see the weight of that principal component by the fraction of the variance that it is capturing in terms of sigma 1 divided by the sum of sigmas. And that is all about principal components and principal directions. Now, the product of singular values, much like the product of eigenvalues, is the determinant of the matrix. That is also easy to prove using the fact that the determinant of a product is a product of the determinants. So A is a decomposition, so there's a product of 3 matrices. The determinant of A is a product of the determinants of the 3 matrices, but U and V are orthonormal matrices, so their determinants are going to be 1. So it's the determinant of A is going to be the determinant of the singular values matrix, but the determinant of singular value matrix, that being diagonal matrix, it's a product of the diagonals. Of course, this applies only to square matrix A because you cannot take the determinant unless it is square. So we never really proved that the determinant of a product of matrices is a product of the determinants of those matrices. The determinant of AB is A determinant times B determinant. That proof is not trivial. I think that is a bit involved. So another one for a 2 by 2 matrix, but there is one more thing. The singular values are going to bracket the eigenvalues. Now let's